Ladies and gentlemen, it is my first and foremost duty to welcome all of you. On behalf of our society, college, and Department of Mathematics, I wholeheartedly welcome an elder but very younger in work, today's resource person, Professor S.S. Bhoosnurmath sir, retired professor, Department of Mathematics, Karnataka University, Dharwad. Welcome you, sir. Next, on behalf of our department, I extend my warm welcome to the principal of our college, Dr. M.M. Huruli sir, Vice Principal, Dr. R.G. Kharabe sir, PU Principal, Dr. S.V. Sulbana sir, IQAC Coordinator, Dr. B.S. Kamble sir, and other dignitaries. Next, I welcome backbone of the Department of Mathematics, HOD ma'am, Dr. M.M. Shankrikop. Last but not the least, I welcome all the participants to this session. Now, I request Dr. M.M. Shankrikop ma'am to introduce today's resource person, Professor S.S. Bhoosnurmath.
Good morning to all. Chief Patron of today's webinar, Sri Amarana Bhagyavadi, respected Principal, Dr. M.M. Huruli, Vice Principal, Dr. R.G. Kharabe, Honorable Resource Persons, Dr. S.S. Bhoosnurmath, and Dr. R. Hilbert, IQAC Coordinator, Dr. B.S. Kamble, learned colleagues and dear participants. It is my great privilege to introduce our today's speaker and my best teacher, Dr. S.S. Bhoosnurmath, sir, Department of Mathematics, Karnataka University, Dharwad. Sir was born on 23/12/1947, completed his MSc from Karnataka University, Dharwad in the year 1970, and PhD from the same university in 1975. Since then, he worked there in Karnataka University, Dharwad in different capacities, and he retired in the year 2010. Awards and honors. He awarded V. Ramaswamy Iyer Memorial Award of Indian Mathematical Society Conference held at Jabalpur for the year 2006. Evaluated as a best teacher by the students in the Department of Mathematics, Karnataka University, Dharwad. Invited talks. He delivered several invited talks at Baroda University, Indian Institute of Technology, IIT Bombay, Lucknow University, Lucknow, Central University of Rajasthan, Shivaji University, Kolhapur, Mangalore University, Mangalore, Kuvempu University, Shimoga, Gujarat, Aurangabad, and Gulbarga. He also delivered plenary talk at the International Conference, Hanoi University, Vietnam in the year 2001, and Sela University, Busan, South Korea, 2002. Worked as a member of academic bodies. Sir was the life member of Indian Mathematical Society, Ramanujan Mathematical Society, Indian Academy of Mathematics, Indore, and Bharat Ganit Parishad, Lucknow. He was an editorial board member for the American Board of Institute, that is ABI. Governing body of editors has included his name for the biographical inclusion in 7th edition of 500 Leaders of Influence. He was the reviewer for Maths Reviews USA, reviewer for Gentrablatt Maths Reviews Berlin, Germany, and elected as a fellow of the Forum D-Analysts Madras. Research experience. Under his guidance, 15 students awarded PhD and 18 MPhil. Publications. Totally published 76 papers, 48 national, 28 international. In his tenure as a convener, the Department of Mathematics conducted national conferences on analysis and its applications for the year 1998, 2005, and 2006. He completed 2 projects, UGC SAF from the year 2003 to 2006, and 1 major project, that is from 2009 to 2012, DST project. His areas of research, complex analysis and Abelian theory, exceptional and deficient values of meromorphic functions, normal families, fixed points, complex differential equations, uniqueness theorem. A noteworthy recent research work, Kit-Wing use conjuncture was solved with Milind Kulkarni, and the paper was published in the journal, that is with the co-authors that is Kick-Wing and M.N. Kulkarni, on the value of distribution of two differential monomials, analysis 99, and in the journal Oldenburg, Verlog, Munchen in the year 2008. And another important paper published along with, again, that is Renuka Devi Dhanar Madam, that is uniqueness and value sharing of meromorphic functions, computer and maths with applications in the year 2007. Sir has published 4 books, and 3 books are for the BSc 1, 2, 3. It is useful for the Karnataka University as well as Rani Chennamma University students, and one more, that is the calculus, and it is along with the co-authors Salimat sir and Setia sir, and it is for the Indian universities. He is encouraging even the students by awarding gold medal. He has instituted a gold medal in his name at the Karnataka University Dharwad during the year 2007 for the students scoring highest number of marks at the MSc in complex analysis. Even after the retirement, he is appointed as an honorary professor at Rani Chennamma University, Belagavi from 2011 to 2013. Even now, he is working as a visiting professor at Central University, Rajasthan from 2010 onwards, and working as a visiting professor at Central University, Gulbarga from 2011 onwards. His one special feature is whenever or wherever he used to talk, he always explains with chalk and board. Today, first time we are seeing he is giving a talk on PPT as it is unavoidable. We know that perfect numbers are like perfect men are very rare. Such a man we had today, that is our Sir Dr. S.S. Bhoosnurmath. With this brief introduction, I place before you Dr. S.S. Bhoosnurmath sir. Thank you one and all.
Thank you, ma'am. We feeling blessed to have such an eminent personality with us today. Now it's a time to listen to the words of resource person. I request Bhoosnurmath sir for his valuable words.
Sir, you just unmute yourself.
Okay, I have muted. It is mute.
Now,
Shall I talk now?
Yeah. You are audible and you are visible also, sir. Over to you. Everything is with you now.
Okay, thank you. Thank you. So, at the outset, I thank the organizers for their kind invitation. And I also thank for your nice words. The topic that I have chosen today is the Riemann hypothesis, or a challenge for the 20th and beginning of the 21st century. Because since last 160 years, this problem has been open in spite of the great efforts of the mathematicians like Fermat, Riemann, G.H. Hardy, and others. So my main aim here is to have brief eye view of the Riemann hypothesis, because it is a 160-year-old problem. We divide the talk into the following points. Number 1, what made Riemann to announce his Riemann hypothesis and his brief history. Number 2, Hilbert's announcement of Riemann hypothesis in 1900, again, a very significant announcement. It gave great impetus to the problem. Number 3, Euler's history and the work on real Euler function, or later called the Zeta Function. This all was the foundation for the work of Riemann. Then number 4, Mengoli's work, not that popular figure in the history of mathematics, but he appeared during the time of Newton. But his work is very significant, and this became ultimately the foundation for, I should say, Euler's work and as well the Riemann's work. And this led to ultimately the Riemann zeta function. So we shall talk about Riemann zeta function in details when we look at the slides. Mangoli posed a very beautiful problem called the Basel problem, which was solved after 90 years by Euler. Well, Ramanujan also enters into the picture in a very peculiar way. Well, he says that zeta is the Riemann zeta function. The value of this at -1, which is 1 plus 2 plus 3 and so on, is equal to -1 by 12. This defies our logic. Looks very absurd, right? And look at the left-hand side, it is a highly divergent series. And a series of positive terms, but the right-hand side is -1 by 12. Everybody thought that it was a wrong result, but his guide, G.H. Hardy, later on proved that this was correct because of the zeta function. We shall talk about this little later when we deal with the slides. Well, in the 6th point, we have the technicalities of Riemann hypothesis and other details. So in 1859, we go back almost 161 years backwards. Riemann published his seminal landmark paper, 8-page paper on the number of primes less than a given magnitude. Well, this is actually the prime number theorem, very famous theorem, which was open for nearly 100 years. Well, Riemann studied several properties of the complex Riemann zeta function and made an observation about zeta S belonging to C, the whole of the complex plane, that all the non-trivial zeros, please note, non-trivial, there are trivial zeros also, they lie on the negative x-axis, whereas non-trivial zeros of the zeta function lie on the critical line in the complex plane called the half line. Half line is the line at the point half in the complex plane and perpendicular to the x-axis. That is called the half line, or later the critical line. Well, Riemann could not prove this, and therefore he called this as a Riemann hypothesis. For him, this appeared that the result is 100% true, but he could not prove it. Well, Riemann lived hardly for 39 years, from 1826 to 1866. Due to his ill health, he suffered throughout his life. Well, 1851, he got his doctorate in complex analysis at the age of 25 under the guidance of Professor Gauss. Well, in his thesis, CR equations were there and Riemann mapping theorem was proved. Very significant results of complex analysis, they come from his thesis. Well, he was a master in complex analysis. Likewise, in real analysis, at that young age, he had to his credit the Riemann integrals. So he was very strong in real analysis also. Well, unfortunately, the king of mathematicians, Gauss, his guide and the head of the department there at Göttingen, the university, said you give a seminar on geometry. 1 month's time was given. He worked very hard and gave a seminar in 1854. Well, that contained a new idea, a revolutionary idea in geometry. He used the metric called the hyperbolic metric and revolutionized the whole of geometry. And a new geometry called Riemannian geometry was also born. Einstein later used the Riemannian geometry to establish his theory of relativity. Well, 1857, he failed to become professor at Göttingen because 1855, his guide, Gauss, died and he thought he would get the position. But that did not happen. His another teacher, Dirichlet, took over as the professor and head of the department. But unfortunately, after few years, he also died and he became full professor in 1859 at the University of Göttingen. Well, 1862, after getting his professorship, he married and a daughter was born out of this marriage. Well, 1866, unfortunately, within no time, 4 years' time, fled from Göttingen because of life threat, as he was a strong Protestant. He left Göttingen and later died of tuberculosis, right, the same year. Then we shall go to the next mathematician, Euler. Also plays a very important role in the development of the Riemann Zeta function. All the basic work was done by Euler. But before that, Hilbert announced the Riemann hypothesis again in 1900. This was an important event. Everybody's attention was turned towards the Riemann hypothesis. Hilbert thought that the Riemann hypothesis was very simple and the so-called Hilbert number, 2 to the power √2, was very difficult to prove. But 2 to the power √2 was proved in 1934 to be transcendental during the lifetime of Hilbert, and then his attention was drawn to Riemann hypothesis. He thought that the Riemann hypothesis was very difficult to prove. Well, Hilbert, a French mathematician, right? Hilbert spaces and all that axioms, they come from Hilbert, the mathematician. In 1900, at the International Congress of Mathematicians, held at Paris, announced 23 open problems. Of these 23 problems, a Riemann hypothesis was the 8th one. These problems gave a direction to the future mathematicians for the next 100 years. Just imagine, next 100 years. Hilbert said about Riemann hypothesis, a beautiful quote, right? He says, Hilbert, even after 1,000 years, if I am awakened from my grave, I would turn up and ask, is the Riemann hypothesis solved? Thus, Hilbert brought to the limelight the Riemann hypothesis and its importance. Initially, Hilbert thought, again, was the easiest, but he realized that it was so difficult because in his lifetime, 1934, Hilbert number is transcendental was proved. The next third point, I say a few words about the mathematician, great mathematician, Euler. Euler prepared the ground for the Riemann Zeta function and the Riemann hypothesis, right? It all began with the work of Euler, 1707 to 1783. Euler was a Swiss mathematician born in Basel, Switzerland. It's a beautiful place, Basel. His birthplace. Euler, Gauss, and Riemann were called three greatest mathematicians of the world. Euler was called the Shakespeare of mathematics. 1727 to 1783. For 56 years, just imagine, he continuously wrote mathematics, right? And he was called a prolific writer. More than 100 volumes worth of mathematics he wrote. He wrote 3 books also. The first one was differential calculus. The second one, the integral calculus. The third one, real analysis. Euler solved the Basel problem. I was talking about Basel and his birthplace. There is a problem named after him, posed by another mathematician. We shall talk about that also a little later. Right? He solved a 90-year-old problem was solved by Euler. Several great mathematicians also tried to solve this problem, right from Leibniz, of course, and Bernardi brothers. They all tried, but they could not. Ultimately, Euler solved that Basel problem. We shall talk about the Basel problem when we deal with the slides later on. Then John Bernardi was his research guide. There were 8 Bernardis. Each one of them was a mathematician. And Euler came to know about the Basel problem through his guide, John Bernardi. But Euler was so unfortunate in the sense that his right eye was very weak. I should say he was almost blind in the right eye. And last 17 years of life, he lost the other eye also. He was totally blind. Just imagine, for 17 years, he just imagined mathematics, made calculations in the mind, and then dictated mathematics. Very unique mathematician for the last 17 years. I shall mention about Mengoli. We have not heard much about this mathematician. It seems he arrived much earlier than Newton, or maybe a contemporary little elderly person than Newton and Leibniz. Mengoli's work from 1626 to 1686 an Italian mathematics laid foundation for the Euler function, and later on Euler function laid foundation for the Riemann Zeta Function. Mengoli did very significant research work. Well, in 1640, right, when even Newton was alive, he posed the Basel problem, Basel, in which Euler was born. Why the problem is called Basel problem, I don't know. This problem inspired Euler. Well, Mengoli proved that the harmonic series, well-known harmonic series we learn in colleges, is divergent, right? But alternating harmonic series, alternatively positive and negative terms in the harmonic series, right, becomes convergent. And he also showed very significantly that its sum is log 2, right? Then, taking a cue from this result, he posed a problem called the Basel problem. I was talking about earlier also. That the Riemann zeta function evaluated at 2 is summation 1 by n square is convergent. He proved it. But what is the exact value of this infinite sum? He posed this problem in 1640. Just imagine, right? Log 2, the alternating sum, series sum, he questioned this part, and it remained open for 90 years. Well, very surprisingly, Ramanujan also enters the scene in the Riemann hypothesis. Well, how? Well, look at one of the results of Ramanujan. He says, without proof, of course, with his strong intuition, he always talked to infinity. That's what people say. That zeta of -1, zeta was not there. He was not familiar with zeta, but we shall use that notation, which is 1 plus 2 plus 3 and so on. The left-hand side is highly divergent, is equal to -1 by 2. Left-hand side, each one of them is a positive term, but right-hand side, it is -1 by 2. This defies logic and looks very absurd to all of us. But this was later confirmed by his mentor, Professor G.H. Hardy. Well, he said, while analytically continuing the Euler zeta function or the Euler function to the whole of the complex plane, well, one can see or prove this in a very simple way. We shall have a look at the proof also when we look at the relevant slide later. Well, Ramanujan says, this also is rather peculiar, Lord Ganesha has dictated this formula in my dream. So this is all about the background of the Riemann hypothesis. I shall now go into the technical details and also the other details of the Riemann hypothesis with the help of the slides that I have prepared. Slides, please. Well, this is the Riemann hypothesis. I am Professor Subhas S. Bhoosnurmath from Karnataka University, Dharwad, a retired professor. Please. Next, please. Well, this is all I have explained during my introductory lecture. Yeah, please carry on. Next one. Yes, please. Root 2 is also transcendental. Yes, please, the same slide. It has disappeared. First one, next.
Sir, 1 minute, sir. So there is a little
Yes,
bit
next
network
one.
problem. Ha, sir.
Next lecture plan and then achievements of the 21st century, 20th century. Next one.
Next.
No, before this.
Before.
No, before this. Yes, before this. Yes,
Okay,
20th and 21st century. Gelfond proved e to the power pi is transcendental, and the Hilbert number 2 to the power 2 is also transcendental. Well, Bibelbach's conjecture was proved in 1984 by Louis de Branges. Four-color problem was proposed by Mobius and proved by Haken and Appel in 1976. 125-year-old problem was solved. Then number 4, Fermat's last theorem was proved by Andrew Wiles in 1994. A 350-year-old problem was solved towards the end of the 20th century. Yes, please, next one. Yes, number 5, prime number theorem I was talking about was solved later by Hadamard and de la Vallée Cousin in 1896. In 1859, Riemann, started proving the problem, prime number theorem, but he could not do it. In 1896, using the ideas of Riemann, Hadamard and Poussin simultaneously proved this 100-year-old problem. Well, Perelman in 2003, a Russian mathematician, solved Poincare conjecture. This was also a 350-year-old problem. Just next one, please. Yes, on August 8, 1900, David Hilbert delivered his historic speech at the International Congress of Mathematicians in Paris and proposed a list of 23 problems, now called Hilbert problems. He thus directed the work of several leading mathematicians of the world. This revolutionized the very way of thinking of the 20th century. Yes, please. Next one. Yes. After 19 years, that is 1990, Hilbert again referred to the following three main problems because these problems very much interested him. And of these, Hilbert problem also appears, right? And Riemann hypothesis was his first priority. Fermat's last theorem, which was proved in 1994. Hilbert number 2 to the power root 2 transcendental was proved in 1934. So only one, the Riemann hypothesis remains open even today. The next one. Well, the $7 million problem, the New Clay Mathematics Institute offers, USA offers $1 million for each one of the problems. I will not go through the list, but only the first one, P versus NP problem, but the very second is the Riemann hypothesis. Yes, the next one. Well, Riemann hypothesis is still open since 1859. Why? We shall try to understand a bit about the nature of the Riemann zeta function, because Riemann hypothesis heavily depends on the Riemann zeta function. So in order to understand this zeta function, we must try to understand the gamma function, not the real gamma function in the complex plane as a meromorphic function. And to understand the gamma function, because it is very closely related to the Riemann zeta function, Weierstrass defined the so-called primary factors. These are the primary factors. EZB is equal to 1 minus Z, e to the power Z plus Z square by 2, plus so on, plus Z to the power P by P, where P is a positive integer. And if P is equal to 0, you see that it is simply 1 minus Z. And look at the function EZP, defined this way, is an entire function. For every Z, it is analytic, whole of the complex plane, analytic, with only one simple 0 at Z is equal to 1. That is obvious from the definition itself. Next slide, please. Well, using Weierstrass factorization theorem, we can extend the real gamma function to the complex gamma function as, you see, gamma Z is equal to e to the power minus gamma Z by Z, the product, infinite product, of course, 1 plus Z by n to the power minus 1, e to the power Z by n, where gamma is a constant chosen so that gamma 1 is 1. This restriction is very important. Well, next one. This gamma that appears in the complex gamma function, when put Z is equal to 1 in that equation and simplified, we get an expression for gamma, which is a constant, well, lying between 0 and 1, which is equal to log of the product 1 plus 1 by n to the power minus 1 e to the power 1. Because of log, that product becomes infinite sum here in the next place. That infinite sum is the finite sum with the n tending to infinity. With a simplification, it is this. And in the next step, it is this. And we go to the next page. This is equal to limit of the last one as n tends to infinity. That n plus 1, log n plus 1, we can also replace it by log n, is the observation of gamma, the Euler mathematician. This is a constant, very peculiar constant again. I think more peculiar than the pi and e. The value is limit as n tends to infinity of 1 plus 1 by 2 plus 1 by n minus log n as n tends to infinity. Euler observed that this exists as a real number, exactly approximately equal to 0.5772 and so on. the approximate value of gamma to 20,000 decimal places has been found using the computers. And therefore, the open problem is, it is still open whether gamma is rational or irrational or transcendental. It is a wild guess that gamma is transcendental. It's a beautiful result, and this constant is due to the mathematician Euler. Next one. Well, I was mentioning about Basel, the birthplace of Euler, and Basel problem. Origin of the zeta function and the foundation for calculus lies, I think I should say, in this, the work of Mengoli. Well, P. Mengoli, 1626 to 86, you can see his photograph on the left-hand side. Right-hand side is the city Basel, which is on the banks of a river, Basel River. Well, next one. So about the Basel problem, well, he was a professor at the University of Bologna, 1647. He served for next 39 years. Throughout his life, till his death, he was a professor of mathematics at that university. Mengoli proved, I have already mentioned it, harmonic series is divergent, whereas the alternating harmonic series converges to log 2. That I have mentioned, 1 minus 1 by 2 and so on is log 2. Then he posed the problem, now called the Basel problem. This is exactly the Basel problem later, after 90 years, solved by Euler. Summation 1 by n squared, which is zeta of 2, 1 plus 1 by 2 square plus 1 by 3 square and so on, converges. But Mengoli proved this, that it is convergent series. But what is the value of the sum? And this was a great problem. Great mathematicians have tried their hand at it. And unfortunately, after 19 years, even Newton and Leibniz, they have tried this. And calculus was also born out of the work of Mengoli. We have not heard much about Mengoli. Yes. Next. Well, Leibniz and Johann Bernardi, and even some Bernoullis, tried to solve the Basel problem. Many mathematicians, great mathematicians, have tried their hand. In fact, it is said 8 Bernoullis were mathematicians, right? Euler, from 1707 to 1783, born in Basel, it was his birthplace, was a Swiss mathematician. He came to know about this problem through his research guide, Johann Bernoulli. While in Basel in 1734, Euler solved this problem and showed that zeta 2 is convergent as known, and he showed that the value is pi square by 6 after 90 years. See, very curiously, pi appears in this equation. Zeta s, the Euler zeta function, for real part s greater than 1 is defined by summation 1 upon n to the power s. But later on, s belongs to C is also admitted with real part s greater than 1. That means Euler also extended his function to the complex plane, but with a restriction, real part s greater than 1. That is on the right of the one line. Yes, please. After more than 100 years, in 1859, Riemann published an 8-page paper on zeta function. Zeta function is actually the extension of the Euler's function to the complex plane, and used it to find the number of primes less than a given magnitude and made a significant progress. This is actually the prime number theorem. He tried to solve the prime number theorem, but he could not do it, right, in 1859. But he posed several problems that the Riemann zeta function was very hard to break. He could obtain several properties of the zeta function, but one he could not solve, and that remains as the Riemann hypothesis. But this problem was solved in 1896 by Hilbert and de la Vallée-Poussin independently. This was mentioned earlier. Next slide, please. Well, this is the picture of Euler. You can look at the right eye, which is almost damaged, very poor eyesight. Later on, he lost his left eye also for the last 17 years. Was a great mathematician. Remarkable work he has done on the zeta function. Sometimes it is called the Euler function because before Riemann, he could obtain several important properties of the zeta function. Zeta S is summation 1 by n to the power s, convergent for all real numbers s greater than 1, and s is equal to 1 is a harmonic series, right, which we have seen is divergent. We shall go to the next one. Yes, Euler also showed that zeta s can be expressed by a convergent infinite product. This is a stunning result, right? And the formula is zeta s is equal to 1 upon 1 minus 1 upon 2s into 1 upon 1 minus 3 to the power s, right, into 1 upon 1 minus 1 upon 5 to the power s, and so on. A product. In other words, it is a product from n from 1 to infinity, 1 minus 1 upon Pn to the power s, where each Pn is a prime running over the prime numbers. One appears for the first time in the Euler's book, Real Analysis. Yes, next one, please. Well, German mathematician Riemann, a pioneer of modern mathematics, treated in 1859 zeta s, the Riemann zeta function. So again, this zeta s is equal to summation 1 by n to the power s is analytic for a real part of s greater than 1. He took the same Euler's function for s complex but satisfying the condition real part s greater than 1. And his ingenuity was that the zeta function was extended to the whole of the complex plane by analytic continuation. That was the beauty, not the restriction real part of s. In fact, the zeta function is defined for the whole of the complex plane. As shown by Riemann zeta s extends to C as a meromorphic function with only a simple pole at s is equal to 1 with residue 1, and it is given by this expression, the last expression. Left hand side you can see s, but on the right hand side s is replaced by 1 minus s. This identity holds for all s. Yes, please, next one. Well, we define the function values for zeta s less than or equal to 0. Between 0 and 1, it was not a problem, but the real problem was to define zeta on the left-hand plane about the x-axis, the y-axis. A functional equation relates zeta s to zeta 1 minus s. Another equation like this on the right-hand side, you see that in place of s on the left-hand side, in most of the places, s minus 1, right? So real part, this is true for real part s less than 0, was observed by Riemann, right? On the right-hand side, you see all these values are well known for all values of s. But if you look at the last pair, if real part s less than 0, then automatically one can easily show that equivalent condition. Real part of 1 minus s is equal to 1 minus real part s greater than 1. Real part of something greater than 1, the Riemann zeta function is well defined. The right-hand expression holds for all s, therefore plugging in this information, one can define the Riemann zeta function on the whole of the complex plane. This was the observation of the great mathematician Riemann. Well, properties of the Riemann zeta function, these were all proved by the great mathematician Riemann, but he was stuck while proving something about the non-trivial zeros. Let us first talk about the trivial zeros of the Riemann zeta function, zeta x. They occur at the negative even integers and they are all simple. Negative in the sense, well, at -2, -4, -6, all the trivial zeros of zeta occur. That means zeta of -2k is 0 for positive integer k. Well, we give a simple proof of this by using the Riemann's functional equation. Zeta s is equal to the right-hand side. And in the right-hand side, put s is equal to -2k, where k is a positive integer. So zeta of -2k is equal to the expression on the right-hand side, and sine of -2k pi by 2 cancels, and we have sine of minus k pi, which is minus sine of k pi, and sine of k pi is 0, and the rest all terms are non-zero terms because zeta is on the right of the line 1, right? Therefore, this whole thing is 0 for zeta of -2k that I have explained in the next slide. Well, you can see that. And if I look at zeta dash, the derivative of that at -2k, we get the quantity on the right-hand side, which is non-zero, obviously, because zeta of 1 plus 2k is a non-zero, and therefore, it is a simple zero. Each one is a simple zero, right? And zeta of s is never 0 for real part s greater than 1, right? On the right half of the one line, zeta has no zeros. So next page, please. We have made the observation taking s is equal to sigma plus it. I shall hurriedly go through this. Taking modulus and also the Euler's product formula involving all the primes, we have a thing like this. And n to the power minus sigma is the Euler's function or the Riemann zeta function when sigma is greater than 1, which is convergent, has been established. E to the power some fixed complex or fixed real number is non-zero, and therefore this is greater than 0. Then the third property, zeta s is analytic in C minus 1 and has simple pole at s is equal to 1 with residue is equal to 1. So this is a beautiful thing. We go to the next page. It is zeta s can be written that way. Therefore, there is only one simple 0 at s is equal to 1. Zeta, number 4 property, has no zeros on the vertical line, real part s is equal to 1. Well, while proving the prime number theorem, Hadamard and Cousin proved this fact independently. Number 5, zeta s has no zeros on the vertical line, real part s is equal to 0, right? Number 6, Riemann calculated first 3 non-trivial zeros of zeta s function by hand. He believed that all non-trivial zeros of zeta lie on the half line, real part s is equal to half. This is exactly the gist of the Riemann zeta function, and exactly here Riemann was stuck. Well, number 7, Ramanujan in his notebook sent to GHRD indicated the surprisingly well zeta of minus 1 is equal to minus 1 by 12. You see, this was clarified earlier. And left hand side, you see GHRD, the mentor of Ramanujan. At the center, Ramanujan's portrait is there. On the right hand, Lord Ganesha, because he thought that Lord Ganesha dictated this formula to him in his dreams. Next one. Well, better representation due to analytic continuation is given by Riemann. Zeta s is equal to, you look at the right hand side, for s, s any complex number excepting 0 and 1. In this, if we put minus 1, s is equal to minus 1, right hand side is this, and sign of minus pi by 2 is minus 1, gamma 2 is factorial 1, pi to the power minus 2 is finite, everything is finite, non-zero, and at the end zeta of 2 is exactly the Basel problem proved by Euler, whose value is pi square by 6. You simplify this, you have minus 1 by 12. That says that Ramanujan's equation is perfectly all right, because when the zeta function is extended to the whole plane, we can see this result very clearly. Next one. Well, again, yes, Riemann hypothesis, zeros of the zeta function that are of the form half plus I alpha. Half is fixed, the imaginary part is alpha, belonging to actually C. It's a mistake here in the complex plane. Alpha is a real number, of course. Complex plane are called non-trivial zeros, right? Only these zeros are called non-trivial zeros. Other zeros are trivial zeros. Riemann hypothesis, all the non-trivial zeros of the zeta function lie on the real line, real part of s is equal to half. Next one. Well, critical line and the critical strip. You have a picture. The y-axis is the 0 line, perpendicular line. And at 1 also there is one perpendicular line. The strip between 0 and 1 is the critical strip. And the strip, the line at half is called the critical line. So all the non-trivial zeros of the Riemann zeta function lie on that red line, the critical line or the half line. That is the Riemann hypothesis. That appears to be true, but so far nobody has proved this. Yes, next one. Well, we shall go to this. Haven't people tried to prove the Riemann hypothesis? Well, hundreds of researchers have tried their hands at the proof. The problem is stubborn. Why it is so difficult to prove is the natural question. The Riemann zeta function is so difficult beast to work with. Well, but in spite of that, 1914 English mathematician and theorist and also the mentor of Ramanujan, G. Hardy, proved that an infinity of zeros of zeta s lie on the real part s is equal to half. Infinitely many zeros lie, but not all. Therefore, the problem remained open. In 1956, well, Lemmer proved that several thousands of the zeros lie on the critical line. Yes, please. Well, look at the picture. In 86, Riemann zeta function, of course, the distribution of the zeros was calculated using the computers. They lie on the critical line, all of them, not even a single zero, non-trivial zero is in the strip, exactly on the line, half line. And then they are symmetrically situated above the x-axis and below the x-axis. That also you can observe. But so far, this has been open, and let us hope for the proof soon. Okay, next one. When 35, 36, Titmarsh observation, not that important. Levinson's also, and Conry, that 2/5 of the zeros of the Riemann zeta function lie on the critical line, not that important these days. Well, of course, next one. Special note about the Riemann hypothesis, because it is related to the prime number theorem. Prime number theorem can be expressed by equation 1 and 2. Pi x asymptotic to x by log x. Why? A quantitative picture is given. Pn, or equivalently, Pn is asymptotic to n log n. Pi x denotes the number of primes less than or equal to x. And Pn, the nth prime number when they are listed in the increasing order. Next one. This is the prime number theorem. Giants like Euler, Gauss, Legendre, Dirichlet, Shapiro, Riemann, Hadamard, and Poussin are associated with this problem. This remained open for 100 years, just imagine. In 1896, Hadamard and Poussin proved this theorem independently. 1859, of course, Riemann made significant progress towards the proof of the prime number theorem. The whole material of Riemann was used by Hadamard and Poussin. That became the foundation. He attacked the problem in a very novel way by using Euler's infinite product. So Riemann knew that this complex zeta function contained all the properties of the prime numbers. This was surprising. Nobody anticipated this, but Riemann could see it very clearly, and that 1859 paper was written. Yes, next one. Zeta function exists as a meromorphic function in the entire plane. Only one pole at z is equal to 1. Zeta s has no zeros in real part, s greater than 0. Hadamard and others, they have proved this part. That was a great achievement, of course, later on. Yes, please, next one. Well, about the Basel problem I was mentioning, Riemann zeta function. Well, Euler found that zeta of 2 is pi square by 6. Pi appears in a very peculiar way, right? And zeta of 4, pi to the power 4 by 90, and so on. Zeta of 8, pi to the power 8, divided by 9450. Everywhere pi appears. And on the left-hand side, zeta of even integers, 2, 4, 6, 8, 10, and so on, right? For 3, what happens? He never knew. Euler could not do that. This next one. But 1979, later, Aperi has stunned the mathematical world with a miraculous proof that zeta of 3 is 1 plus 1 by 2 to the power 3 plus 1 by 3 to the power 3 plus so on, which is approximately equal to 1 point. This is irrational. He has proved this, right? But for 5, 7, and so on, other odd integers, removal tried the proof, but somehow people have not accepted that, and therefore, for odd positive integers other than 3, the problem is still open. Yes, next one. Well, if Riemann hypothesis is true, counting the number primes in any given range of values, our Riemann hypothesis could unlock the mysteries of prime numbers. Number 2, determine the properties of the prime distribution, such as the size of graphs between consecutive primes. 3, develop new primality tests. Contract counting functions for the types of numbers. The 5th one is very important. Strengthen corrections from number to other disciplines such as probability theory and quantum theory of mechanics. Next one. Well, present status of the Riemann hypothesis. What is happening to? Are we very close to the solution of the Riemann hypothesis? Well, Michael Atiyah, who expired very recently, was a contemporary mathematician. We have seen him at Bangalore. An esteemed mathematician announced his proof of Riemann hypothesis in a lecture at the Heidelberg Laureate Forum in Germany on September 24, 2018. Well, Atiyah has won, is not an ordinary person, won the Fields Medal and also the Nobel Prize. Many mathematicians have expressed skepticism about the proof, and therefore the Riemann hypothesis still remains open. Yes, please. It may require new methods and new mathematics at all. These are all the references. Next, please. Thank you. Thank you very much.
Thank you, sir.
Oh, thank you.
Now I'll request the participants. You can interact with sir.
Well, that thank you slide is there. Can you remove it?
Yes, sir.
Yes. Yes, you can start now.
Sir. Hello, sir.
Yes, please.
Sir, some participants have put questions in chat box. One question I will read you.
Yeah, please.
Vijaya Ramani asked the question, how to use complex analysis in daily life?
In the daily life, of
Yes,
course,
sir.
Most of the equations, differential equations that we see, right? The solutions are always, you see, the complex. Though you have a real differential equations, solutions behave in a very peculiar way. And the solutions of the differential equations, you know, they come out of our physical nature of the world. Therefore, it may not be direct, but indirectly, it is definitely useful. Not only that, in many branches of mathematics, and later on, even quantum theory of mechanics, it is going to play a very big role. Already, complex analysis has entered physics to a great extent. Yes.
Next.
Sir. Sir, another one question.
Yes.
Someone, Mary Shaila asked, can the study of the pandemic be graped using complex analysis structure?
Well, it heavily depends on the study of the pandemic.
Yes, sir.
It depends on the compound interest, surprisingly. And compound interest with certain rate of interest, it becomes double and all that. But if we study the pandemic, well, it grows very fast. And once it starts descending, the fast descent will also be very fast. That's how the exponential growth works. Right? That is the answer for this question.
Okay, sir. Another one question. Sayan, this is asked, is there any link between complex analysis and abstract algebra?
Abstract algebra. Well, look at a polynomial and look at the roots of the polynomial, right? In several cases, you can form a group using those solutions. And this becomes a part of algebra from that point onwards. Study of roots also is very important. It is studied through algebra.
Sorry, next, one more question is there.
Yes, please.
What type of new maths we expect to solve Riemann hypothesis?
Well, this is a very good question. People have tried and they are convinced now that only the ideas of Riemann, Euler, and others, even including the Mengoli, it appears that it cannot be solved with the present tool of mathematics, right? And what kind of a tool is required to solve the Riemann hypothesis? Nobody knows. Only a mathematician who solves that problem would be giving the solution, the kind of mathematics that is required for the solution. Yes.
Okay. Then another question, sir.
Yes.
So can you give some glance of proof that authors Ataya given?
Ataya failed because he was trying to use the techniques of Riemann, exactly Riemann and Euler. And there is also another function called the Zeta function, the properties of that like the Zeta function, and he failed. So same kind of mathematics will not give the solution for the Riemann hypothesis is very clear from the attempts of Ataya.
Okay, sir.
Okay.
Next, how the Euler product expansion defines to infinity many primes in the form 4n plus 3.
Yeah, you mean the Euler product formula?
Yes, sir.
It is an infinite series, infinite product, like the infinite series.
Okay, sir.
The idea of the infinite product came first from the mathematician Euler. So left hand side, the Zeta function, isn't it? Zeta of S. Right hand side, you have the infinite product of primes. So naturally, the zeta function is associated with the primes. And one can expect all the properties of primes using the Riemann zeta function.
Sir, next ಇನ್ನೊಂದ್ರಿ books care sir. Please suggest good books for the proof of Riemann functional equation.
Riemann's functional equation. There is one book by Shikharji on analysis 2. And that book gives the proof of even the prime number theorem.
Okay, sir.
And he deals with the Riemann zeta function. So many results now that I have talked about have come into textbooks. You can refer to that. One of the books is Simon's books on differential equations.
Sir, ಇನ್ನೊಂದು question ರೀ. What is the secret of mathematical stamina? Not an academic question ಅಂತ ಯಾರು sir? MD Patil sir ಕೆ ಯಾರು sir?
You see, mathematical stamina, according to me, of course, comes from continuous interest in mathematics and doing mathematics throughout your life. I think that gives the stamina. Even at the age of 73, I'm not tired now. Whenever somebody invites me, I will be very happy to come and talk. Though, of course, I'm not much familiar with the talks like this internet, which I don't like personally. Hodelre now. We are traditional teachers.
Questions sir. I think.
ಏನು ಹೇಳ್ರಿ?
Questions ಇನ್ನೂ ಬಹಳ ಅದಾವ್ರಿ. ನಿಮ್ಗೆ ಟಯರ್ಡ್ ಆಗಿರ್ಬೇಕು ಸರ್.
ಏನ್ ನಾ ಟಯರ್ಡ್ ಆಗಿಲ್ಲ. ನಿಮ್ಗೆ ಸಾಕಾಗೋ ತನಕ ಕೇಳ್ರಿ. ಅದ್ರಾಗ ನಿಮ್ಗೆ ಇಂಟ್ರೆಸ್ಟಿಂಗ್ ಅನ್ಸಿದ್ದು ಕೇಳ್ರಿ ಕೆಲವು ಬೇಕಿದ್ರು.
Sir, ಇನ್ನೊಂದೈತ್ರಿ. Does the ring of Gaussian integers introduce any link between complex analysis and abstract algebra?
ಇನ್ನೊಮ್ಮೆ ರಿಪೀಟ್ ಮಾಡ್ರಿ ಕ್ವಶನ್.
Does the ring of Gaussian integers Zi introduce any link between complex analysis and abstract algebra?
Abstract algebra. Well, Gaussian integers is a ring. ಹೌದಾ? Although it is algebra. ಹೌದಾ? But Gaussian integers ಎಲ್ಲಿಂದ ಬರ್ತಾವು? ಅವು ಕಾಂಪ್ಲೆಕ್ಸ್ ಪ್ಲೇನ್ದಿಂದ ಬರ್ತಾವು. ಅದಕ್ಕೆ ಡೆಫಿನೆಟ್ಲಿ ಲಿಂಕ್ ಅದೇ ಅದ್ರಾಗ.
Yes, sir.
ಮತ್ತೇನು ಹೇಳ್ರಿ?
Has Riemann geometry any association to Riemann hypothesis?
In a way, no. Riemann hypothesis is on the complex plane. ಆಮೇಲೆ Riemannian geometry is the geometry using the hyperbolic metric. ಅದಕ್ಕೆ ಅದು ಯುಕ್ಲಿಡಿಯನ್ ಟು ನಾನ್ ಯುಕ್ಲಿಡಿಯನ್ ಜಾಮೆಟ್ರಿ ಅದು ಕನೆಕ್ಷನ್ನು, ಇದು ಬೇರೆ. ಅದಕ್ಕೆ ಒಂದಕ್ಕೊಂದು ಸಂಬಂಧ ಕಲ್ಪಿಸೋದು ಬಹಳ ಕಷ್ಟ ಅಂತ ನಾನು.
ಓಕೆ ಸರ್.
ನೀವು ಸಮೇತ್ ಚೌಗ್ಲೆ ಅಲ್ಲ?
ನಾನು ಸರ್.
ಆಮೇಲೆ ಇಲ್ಲಿ ಎಣ್ಗೆ ಅವ್ರು ಕಾಣಕತ್ತಾರ, ನನಗ ಬಾರ್ಕಿ ಅವ್ರು ಕಾಣಕತ್ತಾರು, ಆಮೇಲೆ ನಂದ ಫಸ್ಟ್ ಏನೇನ್ರಿ ಮತ್ತೇನ್ರ ಇದ್ರ ಕೇಳ್ರಿ, ಇಲ್ಲ ಅಂದ್ರ ವಿಶಾಲ್ ಚಾಟ್ ಫಾರ್ ಎ ವೈಲ್. ಏನ್ರ ಬಾರ್ಕಿ ಅವ್ರ ಎಣ್ಗೆ ಅವ್ರು ಏನ್ರ ಇದ್ರ ಕೇಳ್ರಿ, ಹಂಗ ಸುಮ್ಮನ ಕುಡೇವಿ ಮಾತಾಡೋದು ಅಷ್ಟ. ಏನ್ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಅಂತ ಅಲ್ಲ, ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಆತಲ್ಲ.
So many participants express their views. So many participants expressed their view and all enjoyed your sessions.
Oh, thank you. Thank you.
And so many are telling it's a very valuable and informative session. So thank you so much on behalf of all the participants.
Oh, thank you very much. Huh?
So,
I'm encouraged. ಯಾಕಂದ್ರೆ ಇಂಥ ಇದಕ್ಕೆ I have not exposed myself.
Sir, this is, I heard that this is your first online session.
ಹೌದು online.
But it's very much, sir, attractive and successful, sir.
No, thank you. Was it understandable or not?
Yes,
Please tell
yes,
me.
sir, yes, sir, yes, sir.
It's
That
like a novel, sir.
No, that is most important.
So
You
definitely
see,
we understood.
I have accepted the offer because I can reach the large number of audience, about 100 at least.
Yes, sir. So
Isn't
100 are on Zoom and even more than that are watching on Facebook, sir, live.
Asma Sankanur raised hand. Is she a participant?
Yes.
Yes, sir.
Asma from Belgaum, isn't it?
Hello.
Yes, please.
Good afternoon, sir.
Good afternoon. Where are you now?
Sir, in Hubli, sir.
Hubli.
Sir, how are you, sir?
You got your MSc from this place, is it? Dharwad?
RCU, sir.
RCU. That means
7 to 13.
you are my
I'm
student.
your student. Ha, sir.
I am so happy to hear you, Asma, after a long time.
Same to you, sir.
Do you have any questions?
Sir, that is only my question. Even I'm studying the Euler product expansion, sir. So, how in that it is going to be, if it is summation 1 by n raised to s converges highly, then it is going to be will make use of infinitely many primes which are in the form of 4n plus 1 and 4n plus 3, sir.
Right.
My question is, how after that, how it is going to be written in the form of log zeta s, sir? That I'm not understanding.
No, actually, I must actually see that.
Okay.
Did I show that? Because I showed the expression for zeta s on the right hand side, the product of infinite number of them. That means it was an infinite product, not an ordinary product.
Yes.
Not a finite product. Like the infinite sum, it was infinite product. Even the gamma function contains the infinite product, infinite sum. Like that, infinite product also is defined by Weierstrass, actually.
Okay.
Then used by Euler very extensively. Very deep result of complex analysis.
Sir, actually, I want PPTs of your today's session, sir.
PPTs, I think you can easily get it from the organizers. I hope Mr. Samej Chogle will tell you.
Yes, sir.
Thank you, sir. Thank you so much.
You can
Okay, participants, we will provide you the PPT.
Yes, please.
Participants, we will provide you the PPT through your WhatsApp group.
After the session, we'll send the PPT to all the participants.
Thank you, sir.
Oh, thank you. Thank you.
One minute. I project the Boreum notebook. Ms. Prajakta Bore, do you have any question? You raised your hand.
Prajakta Bore, if you have any doubts, you can ask. You have raised your hand. You please unmute your audio first. Prajakta Bore, any question? Okay. Now we have, last but not the least, vote of thanks by Ms. Vinya Khoth, lecturer, Department of Mathematics.
Is it audible?
Yes.
A very good afternoon to one and all. I am Ms. Vinaya Khod, member of this webinar. On behalf of KLE GIB College and Department of Mathematics, I take this opportunity to propose vote of thanks for making this such a resounding webinar and for making this successful webinar for 2 days international webinar. First of all, I would like to propose hearty vote of thanks to our today's Honorable Resource Person, Professor S.S. Bhoosnurmath sir, retired Professor of Department of Mathematics, Karnataka University, Dharwad. We are really enlightened with your knowledge and presence, sir. So thank you, sir. Next, I would like to extend a special thanks to Chief Patron Sri Amar Bagewadi, Member, Board of Management, KLE Society. Next, I also would like to express our profound gratitude to our beloved Principal, Dr. M.M. Hurri, and Vice Principal, Dr. R.G. Kharabe, and IPSC Coordinator, Dr. B.S. Kamble, for enthusiastic support. Next, I am very much thankful to our beloved HOD, Dr. M.M. Shantrikov, for her continuous support and advices, which have greatly helped towards the success international webinar. People who have given their precious time in organizing this webinar. So I would like to thank and acknowledge for Dr. Ashok Rathod, convener of this webinar. Next, Ms. Girja Kargupi, organizing secretary. Next, Srimati Geeta Kamte, anchor of this webinar. Next, I would like to thank Sri Sagar Mirje, Mr. Samay Chowle, and Mr. Jinedar Magdum for management and coordination for this technical session. And lastly, I sincerely thanks to all the participants for actively participating for these 2 days international webinar. So once again, I thank all for your cordial cooperation. So thank you one and all.
Thank you. Thank you. So I can leave now, is it? Dogle?
Yes, sir.
I can leave, isn't it?
Yes, sir. Dear participants, we will send the feedback links to your registered email IDs. Please fill the feedback forms. Soon after submitting feedback form, you will receive your certificates. We are not sending link in the WhatsApp group. We are sending in the registered emails only.
Okay. Thank you, sir.
Oh, thank you.
Thank you, sir.
Leave ಆದ್ರೆ ಅನ್ಸುತ್ತೆ sir.
ಇಲ್ಲ ಯಾರಿಲ್ಲ ಲೀವ್ ಆಗ್ತಂತಂದ್ರು ಎಂಡ್ ಮಾಡ್ರಿ ಮೀಟಿಂಗ್ ಎಂಡ್ ಮಾಡ್ರಿ